Okay, so let's start our second unit, which is dynamics. Now, Zach is probably up by now, and he'll be watching this, I'm sure, as soon as it gets posted. Right, Zach? Yeah. So you have a little handout here that says dynamics. I'm not going to spend a lot of time on this. You should, at the very least, you should skim through it. Spend 5-10 minutes skimming through it. Okay, at the very least. Technically, you should read through it and answer these questions. Okay?
This is the unit with like the normal force.
Yeah, I know. You'll be okay, Stephen. We'll get you straightened out.
I'm still arguing.
Yeah, we'll get you straightened out. Okay, so as a quick refresher, okay, so I'm not going to give you any time specifically to do that, but there'll probably be time sort of built in a different place. What I would like you to do is go to the last page of that little handout where it says force and its representation and drawing free body diagrams. Now let's just read this through quick here. Okay, so you've got this handout here. Now you will probably recognize this from grade 11. Just a very quick refresher on drawing free body diagrams. So, free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. A free body diagram is a special example of the vector diagrams discussed in an earlier unit. These diagrams will be used throughout our study of physics. The size of the arrow in a free body diagram is reflective of the magnitude of the force. In other words, big arrows mean big forces. The direction of the arrow reveals the direction which the force is acting. Each force arrow in the diagram is labeled to indicate the exact type of force. It's generally customary in a free body diagram to represent the object by a box and to draw the force arrow from the center of the box outward in the direction that the force is acting. An example of a free body diagram is shown at the right. Okay, so right here. The free body diagram above depicts 4 forces acting upon the object. Objects do not necessarily always have 4 forces acting upon them. There will be cases in which the number of forces depicted by a free body diagram will be 1, 2, or 3, or 4, I suppose. There is no hard and fast rule about the number of forces which must be drawn in a free body diagram. The only rule for drawing free body diagrams is to depict all the forces which do exist for that object in the given situation. Thus, to construct free body diagrams, it's extremely important to know the various types of forces. If given a description of a physical situation, begin by using your understanding of the force types to identify which forces are present. Then determine the direction in which each force is acting. Finally, draw a box and add arrows for each existing force in the appropriate direction. Label each force arrow according to its type. If necessary, refer to the net force help sheet, which you guys probably saw, I think, last year, for descriptions of the various force types and their appropriate symbols. So here's some practice ones which you guys have already done in grade 11. So can you do them again? Quinn. Yes, there is. Let's just talk about this for a second, okay? So here's the example free body diagram right here. We see the F graph, which I tend to label as FW. You always draw the force vectors away from the box. Always away. So gravity is down, FW. Now here's the one that Quinn and Stefan have a great deal of difficulty with. The normal force. Okay? Newton said that for every action force, there's an equal and opposite reaction force, right? So, because gravity is pulling down in the box, right? Or think about my binder sitting here on the table, right? Gravity's pulling down on it. If there was no force up, then there would be a net force on the book, and what would it do? It would fall, right? So there has to be, the net force is clearly 0, it's not moving, so there has to be a normal force, and Stefan is still shaking his head. There has to be a normal force up that's equal to the force of gravity, right? So Stefan's question is, he's dropping a pen or a little remote thingy or whatever it is, right? You're dropping, calculator, book, what have you, right? Okay, you're right. Okay, there is gravity's pulling it down. Actually, there is an equal and opposite force. The Earth is attracted upwards towards the calculator. However, the calculator is pretty small compared to the Earth, so that force is, we can't even see it, right? Like that force on an Earth-sized mass is insignificant.
So how would you get a mass we can see?
So why is there no force on the
Okay, well, is there a net, and when the calculator of the pen is dropping, is there a net force? Is it accelerating as it's dropping?
Yeah.
Yes, it is, right? And we know, I'm just going to make some space here. We know F net is equal to ma, right? Clearly the pen or the calculator has a mass. If it's accelerating at minus 9.8, does there have to be a net force? Yes, there does. And so the pen falling or the calculator falling, the FBD looks like that. There is a net force. When it's sitting on the table, push your pen on the table. Is no acceleration, right? So now the acceleration is 0, which means that the net force must also be 0. Is there gravity pulling down, Stefan? Sure is. So that for the net force to be 0, there has to be an upward force that's exactly the same length, giving us a net force of 0.
So because,
We'll just accept it.
no, because the gravity is pulling it down, what's pushing it up?
The table.
The
table's
table.
not moving though. The table's being pulled up.
Something has to move to push.
Well, not necessarily, but you said the net's 0.
Yeah, the net force is
The
0.
gravity's pulling the pen down, yes, but it's also pulling the table down as well.
True enough.
So then what would be the opposite force?
The floor is pushing up on the table.
The floor is also pushing down the ground. Cement to the pillars, to the sand, to the dirt, to the ground, all the way to the center of the curve.
Okay. I don't understand your argument.
Well, what's pushing back up?
All those
But
things.
it's all pulling together. It's all going down too. Yeah, the floor pushes back on the table, it pushes up the pen, but the pen pushes on the table, it pushes on the floor.
Okay. I see where you get that. Yeah.
We could do it over. Just keep
Yeah, we could. All right. So what I would like you to do is quickly go through these. There's 11 of them. Draw an FBD for each one of those. You've done them before. It shouldn't take you more than 11 minutes. Probably less. Most of these, I think you should have gotten pretty straightforward. Okay. Well, I try to be.
Your net force is the same as.
Yeah, I'll take that as a compliment, Quinn. A book is at rest on a tabletop, diagram the force acting in a book. Well, I hope everybody got that, right? A girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes, diagram the forces. Now, it could be exactly the same. If you want to be, you could say there's actually 2 forces on her because she's got 2 ropes, right? But I'll take a single one. Now, the sum of those would have to be equal to that, right? Mine's not quite. It would be more like that.
So it'd be like happiness.
Yeah.
You have to actually do that. Like, would you mark this wrong?
In grade 11, I care more about it.
But this is more.
It's more, yeah. You guys, I care more about the problems, and so yeah. I think you understand that. So. Unless the question specifically asks for a free body diagram, and that's the only thing, then that might be something that I'd be checking on the question. Okay, so an egg is free falling from a nest in a tree. Neglect air resistance. So we've got just gravity, no air resistance, right? Flying squirrel is gliding, no wing flaps from a tree to the ground at constant velocity. Consider air resistance, diagram the force acting on the squirrel. So there's no wing flaps. There is air resistance, so this is going to be like that, right? And it doesn't say whether it, constant velocity, so what does that mean? It means they have to be equal. Number 5, a rightward force applied to a book in order to move it across a desk with a rightward acceleration. Consider friction.
Yeah, no, I just have to ask if I don't understand the last question.
The squirrel?
Yeah.
Okay.
The reason I'm not still going to argue about the case.
Okay.
He's fault. Why is there that force? Because he doesn't have a wing.
There's air resistance.
Oh, that's the only reason.
Air resistance and it's constant velocity. So that means acceleration is 0, which means net force must be 0.
Means that he has wings that can fly, that control.
Yeah. Well, no wing flaps, it means that he's not actually flying. He's not going up, right? He can only, the most he can do is fall at a constant velocity.
Okay, yeah, that makes sense. You specifically say in questions in a perfect world with no air resistance and all that.
Yeah.
Stuff.
Yeah. Okay, good. A rightward force applied to a book in order to move it across a desk with a rightward acceleration. Consider friction. So here we've got a weight force. We've got a normal force. We've got friction. It's going to the right. There's an applied force to the right. It is, however, accelerating, so that means that the friction force is less than the applied force. Yeah, good. This time here, we've got it at a constant velocity, so basically it's, I'm trying to select all this here. That's, Well, I could have had it drawn by now, couldn't I?
What? Yeah, oh, there we go.
Come on. It's exactly the same with one exception. Because it's a constant velocity, that means that these forces would be the same, right? That's all it means. Constant velocity. Right, Mary? Yeah? Good? Okay. College student rests a backpack on his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces acting on the backpack. Now it's resting, right? The pack is suspended motionless. We've got weight force down, and we would have one strap. We'd have a tension force or an applied force up. Now, if you want to say that it's actually like that, okay, then this component here, FTV, would have to equal this, and then you'll notice that there is a horizontal component, which means the backpack has to be actually accelerating to the right. So it's not likely going to be a situation like that. Well, even still, there would be unless he's accelerating, there would be no horizontal component. Yeah. Maybe. There's some tricky parts, I guess. A skydiver is descending with a constant velocity. Consider air resistance, gravity, weight force, and air resistance. Number 9, loosely packed snow. That's code for there is friction. Loosely packed snow, there is friction. It's applied to the right. It's with a rightward acceleration, so it's going to be like that one we had before. We've got our weight force. We've got our normal force. There's an applied force to the right, and there's a small amount of friction. But there's acceleration, so the applied force is bigger. Now, number 10 is the one that always causes some discussion. The football is moving upwards towards peak after having been booted by the punter. Neglect air resistance. Diagram the force acting upon the football as it rises upward towards peak. Weight force. And nothing else. Nothing else. After having been booted, the ball is in the air. It's not stupid. The ball is in the air. How is my foot applying a force to the ball? Unless I have. What about it?
It's still accelerating up. So
is it?
Yes.
Why? It's moving upward, but it's not accelerating upward.
When you first hit a baseball,
Even if it's slowing down, it's still accelerating.
That's true, but that would be because of air resistance, and it says here neglect air resistance. So if you want to include air resistance in this, it would actually be like that. But there is no big applied force. It's already been booted. It's gone.
That's weird to look at. It's like that is going up in the air right now.
That is going up in the air. Okay? And that's why I put this in here, right? These are the forces that are currently acting on it. It's not its motion. Right? It doesn't show direction. It doesn't show motion. Okay? So watch out for that kind of thing. Cars coasting to the right and slowing down. We've got our weight force. There is no applied force. So watch out. I might say, which way is this car moving? It's going to the right.
That's a tricky one.
Yep, I'm a trickster.
I got two.